Good morning, Joe. Good morning, Joe. How are you doing this morning? I'm doing great, thanks. Oh, good morning, Aaron. I was just talking to myself. I'm glad you're here. Give people a minute, see if we have anybody else joining us for the day. While we're waiting, let's just do a little recap of what we covered on Tuesday. Boop, 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 boop. Okay, so just as a recap, started off just talking a little bit about reminding you about the atomic structure. Every atom is composed of positively charged nucleus surrounded by negatively charged electrons. The nucleus itself has protons, which are positively charged, and neutrons, which have no charge. And I kind of mentioned charge is this property that we noticed that things that have the same kind things that have the same property that we call charge will repel each other. Things that have the opposite property that we call charge attract each other. Positive and negative fundamentally do not mean anything. It's just we know there's two different kinds. Benjamin Franklin's the one who decided to call protons positive and electrons negative. But ultimately what we know is that two protons repel each other, two electrons repel each other, a proton and an electron will attract each other. We call that property electric charge. Went through just a few important facts about atoms. One, we already said, every atom has a positively charged nucleus surrounded by negatively charged electrons. Other important thing is all electrons are identical, as are all protons, as all are neutrons. Meaning, the electrons in my body have the same mass, have the same charge as the electrons in your body, as the electrons in some other object. They're all identical. Protons and electrons have the exact same charge, except protons are positive and electrons are negative, which means an important thing. If an object has the same number of protons and electrons, that object will be neutral. And we talked a little bit about how does an object become charged. It's always by gaining or losing electrons, not protons, because they're trapped in the nucleus. Talked about the fact that opposite charges attract, like charges repel. So if I have a positive and a negative, they're going to attract each other. Two negatives will repel, two positives will repel. Talked a little bit about the fact that if you're going to, let me just go back to the lecture notes real quick. Talked about the fact that if an atom gains an electron, now it has more electrons and protons, it's negatively charged, and we call that a negative ion. So this happens when an atom gains one or more electrons. If an atom loses one or more electrons, now it has more protons than electrons, it's positively charged, we call that a positive ion. And whenever electrons are getting transferred, I went through the fact that it's always the outer electrons that are transferred because they're relatively weakly bound compared to the inner ones. And then it talked a little bit about the difference between conductors and insulators. What is the difference in one sentence? What is the difference in one sentence? Conductors have loosely bound electrons. They have electrons that are not anchored to any particular atom. Insulators, all of the electrons are tightly bound. The reason that matters is because when you hook up a conductor to a circuit, as we'll see next chapter, like if you look at the wires inside the wires here, when there's electricity flowing through these wires, you are not actually getting electricity from the walls or from the batteries or anything like that. What you're getting is the energy to move charges that are already present in the conducting wires. So what makes a conductor is something that has a bunch of electrons that are not anchored to any particular atom. Some kinds of conductors, most metals, so especially copper, aluminum, silver, gold, salt water, tap water, the human body. Insulators, again, are things that hold onto their electrons very, very tightly. Glass, rubber, plastic, wood, pure water. Also touch quickly on conservation of charge. It just says that the total amount of charge for any process remains constant. What it means is if one object is losing electrons, another object is gaining electrons. An object doesn't become charged by creating positive or negative charge. It's always by charge getting transferred from one object to another. So if one object is losing some negative charge, another object is gaining some negative charge. And then the last thing we got through is Coulomb's law. Coulomb's law describes the force between two charges or between two charged objects. The big equation is the force equals some constant, K, Q1, Q2 divided by D squared. Q1 and Q2 is the charge on each particle or the charge on each object. D is the distance between the objects. You don't need to use that equation to solve for anything. Here's what you need to know is one, the bigger the charges are, the more force there's going to be. So if I have something that has 10 times as much charge, the more charge they have, the more force there's going to be. The big thing, though, is the force depends on 1 over distance squared. This means two things that are important. One, the bigger the distance, the smaller the force, which makes sense, right? If I have two charges and the farther apart they are, the weaker the force is going to be. But it depends on the distance squared, which means if I take them and move them 3 times as far apart, the force isn't 3 times weaker, it's 9 times weaker because I have to square the distance to figure out what happens to the force. And then last but not least, we measure charge in coulombs, and a coulomb is a huge amount of charge. It's the charge on 6.25 billion electrons. All right, that was a little 8-minute recap. Before I take off my recap, are there any questions that I can answer about anything I covered on Tuesday? If not, I got a couple questions for you. Gone once, gone twice. Okay, so if you're watching this at home, I'm going to give you a few clicker questions. I'm going to give you the question and then give you about 30 seconds to think about it, and then we'll go through them. All right, let's look at a couple clicker questions. In fact, let's do 3. Let's start with 22.4. Let's do this in red. Particle A and B interact with each other. Particle A has twice the charge of particle B. Compared to the force on particle A, the force on particle B is, so we've been drawing, let's say I've got something here which has a charge, let's say this A, and I've got B. And again, we're not really dealing with Coulomb's law where we're using it to calculate quantities, but let's just say the charge, we write charge as Q. Let's just say the charge was 2 coulombs, even though that's an insane amount. And the charge on B was 1 coulomb. What that would mean would basically mean if this is positively charged, that means it has more protons than electrons, which means it lost a bunch of electrons. And if it really had a charge, let's say of 1 coulomb, that would mean this object lost 6.25 billion electrons, which sounds like a huge amount, but the number of atoms in our body is insane. The number of electrons and protons in our body is insane. Anyway, The point is, if I have these two charges that are each positive, they're going to repel each other. The question is, let's say that particle A had twice as much charge as particle B, or object A in this case has twice as much charge as object B. How do the forces compare? Compared to the force on particle A, the force on particle B is 4 times as much, twice as much, the same, half as much, 1/4 as much. And the answer is, well, here's a hint. You could have answered this question back in chapter 5, not knowing anything about electric charge. And if you remember, chapter 5 was all about Newton's third law. Newton's third law applies to every known force. For every action, there's an equal and opposite reaction. If charge B exerts a force on charge A to the left, then that means charge A exerts the exact same force on charge B, but to the right. The forces are exactly the same, so the answer is the same. It doesn't matter if one of the particles or objects has 1,000,000 times the charge of the other. The force that each charge exerts on the other charge is the same. So this equation that we're not solving, F equals K Q1 Q2 over D squared, this gives the force that each charge exerts on the other one. Okay. Here is a good one that you may see a similar equation or a similar question sometime again in the future. Two charged particles held close to each other are released. As they move, the force on each particle increases. Therefore, the particles have the same sign, opposite signs, or not enough information. So let's just say I have these two particles and I am somehow holding them so they can't move. Now I let them go. As they move, the force on each particle increases. Therefore, the particles have same sign, opposite sign, not enough information. Little hint. If the force increases, what does that tell you about the distance between them? And the answer is, we know the force goes like 1 over distance squared. Or the smaller the distance, the bigger the force. The bigger the distance, the smaller the force. So if the force increases, that must mean they are getting closer together, which means they attracted each other, which must mean they have opposite signs. So again, how do we know that? If I let them go and the force is getting bigger, that means they're getting closer together. If they're getting closer together, that means they attracted each other. If they attracted each other, that means they have the opposite sign. If instead they had the same sign, when I let them go, they would repel each other. So they'd start to move farther apart, and then the force would get smaller. Okay, one more. 22.7. Complete the following statement. When a plastic rod is rubbed with animal fur, the rod becomes negatively charged as A, protons are transferred from the fur to the rod. B, electrons are transferred from the rod to the fur. C, electrons are created on the surface of the rod. D, electrons are transferred from the fur to the rod. E, protons are transferred from the rod to the fur. Now, you should be able to eliminate these right off the bat. 1, it's always electrons that are being transferred whenever an object gets charged. It's never protons because protons are trapped in the nucleus by the strong nuclear force. So I can eliminate A, it's not protons transferred. I can eliminate E. And keep in mind that we have conservation of charge. Charge is always being transferred between objects, but I'm not having charge being created at the surface of a rod or something like that. So I can get rid of C. Now, if the rod becomes negatively charged, That means the rod gained electrons. Well, if the rod gained electrons, then that must mean the fur lost electrons. So in this case, we have electrons are transferred from the fur to the rod. So the correct answer was D. It's always electrons being transferred, and whatever becomes negatively charged is the object that is gaining electrons. All right, booyah. Let me stop this for a second. Nope. What I want to know, what you do how to talk. What I keep my coffee. What I want to do now is talk about the 3 ways of charging an object. So we just talked about an object's always becoming charged by gaining or losing electrons, but how does that happen? And actually, before we go into that, here's a quick question. Does anybody know the only way to make sure an object doesn't charge? What is the only surefire way to make sure an object doesn't charge? You take away his credit card. Ah!
That was funny.
Okay, so first I want to show you a couple slides. PowerPoint. Boop, 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 electrostatics. Shift F. Okay, let me do a new share. Okay, so I'm going to go through this and then I'll go back and write these down so that you can get these. So one, there's 3 main ways of charging an object, of getting one object to become charged because it has more protons than electrons or more electrons than protons. First one, charging by friction. And again, I'm going to go through this quick and then write it down. This is where electrons are transferred when one material rubs against another. So I showed you that I could rub a plastic rod with wool and get electrons transferring from the wool to the rod. That's an example of charging by friction. 2, charging by contact. So this is if I already have an object which is charged, I can touch it to another uncharged object to charge it. So if I've already charged this rod, charging by friction, and then I go and touch another object with it, that's charging by contact. If this is already charged, and then I touch it to an uncharged object. And then charging by induction is a little bit more challenging, but this is where you are charging one object without touching it to another charged object. It's not charging by friction because the objects aren't being rubbed together. It's not charging by contact because you're not touching it to a charged object. So let's kind of go through these and then I'll write them down. So 1, charging by friction. Let me say that it's not any 2 objects that you rub together are going to get charged by friction. I can't just rub my hands together and have my hands get charged. Chemically, it has to be one object that wants to one object that wants to gain electrons and one object that wants to lose electrons. So it ends up plastic will tend to want to gain electrons. Fur or wool will tend to want to lose electrons. So when I rub the 2 together, I can get electrons being transferred from one to the other. In this case, from the animal fur to the rod. So if you've ever gotten a static shock while walking across a carpet, what's generally happening is charging by friction. Is you are either rubbing electrons from the carpet onto you or from you onto the carpet. I'm not sure which one. It depends on the kind of shoes you're wearing and the carpet and things like that. So you're becoming charged. You're either becoming negatively charged because you're gaining electrons, or you're becoming positively charged because you're losing electrons. You then go near a conductor. Remember, a conductor has electrons that are free to move. So it has electrons that can flow. So in this case, this is showing the person losing a bunch of electrons to the carpet. So the person becomes positively charged. And then when he touches a conductor where electrons can move, they flow onto him. Another example, charging by friction, is just if you ever have rubbed a balloon on your head and then hung it to the wall. What ends up happening is, again, your hair will readily lose electrons. The balloon will readily gain electrons. And so by rubbing a balloon on your hair, you can get the balloon to become negatively charged. And then a little bit later, I'm going to talk about then how the balloon gets attracted to the wall. Charging by contact, like I was saying, is if you have an object which is already charged. Like here, there's a rod which somehow became charged negatively, maybe charging by friction. Now I go and I touch it to an uncharged object, like this sphere. Then I can have the charge being transferred from the rod to the sphere just by touching them together. That's charging by contact. And then charging by induction is a little bit more challenging. In essence, you're charging an object without touching it to another object that's charged and without rubbing it together. So here's a classic case where I've got a conducting sphere. It has a bunch of positive and negative charge in it. I now bring a negatively charged rod nearby, and what's going to happen is the side of the rod, or the side of the sphere closest to the rod, I'm going to have opposites attract. The side of the sphere farthest from the rod, I'm going to have like charges repel. The end result is the charge has separated. Even though the sphere is still neutral, one side is now negatively charged, the other side is positively charged. But as of now, it's still neutral because no charge has left the rod. I'm sorry, left the sphere. But if I then touch it with a conducting wire or a grounding wire, now all of this negative charge can flow off of the wire or off of the sphere onto the wire into the ground. The end result is the sphere has lost electrons. So it ends up becoming positively charged. So I did not touch it to another charged object. I did touch it with a wire. I wasn't rubbing my hands together, so it wasn't charging by friction or charging by contact. If I have time, I'm going to touch on lightning, but let me discard this for a second. Stop this share. A couple things just about charging by friction. So one, if you've ever gotten a shock getting out of your car, this happens basically because in the process of getting out of the car, your butt is rubbing against the seat, charging by friction occurs, and you become either positively or negatively charged. And then when you touch the metal of the door or the metal of the outside of the car, you can get charge being transferred either to you or away from you. And that's when you feel a shock. Happens to me in this one car I had, basically every time I'd get out, I would get charged. And it's just because the fabric of my jeans and the fabric of the seat cover just made it so that charging by friction occurred. Another couple fun examples. I have two younger brothers. One Christmas, my mom got us all the exact same pair of slippers, different sizes, obviously. But these slippers just worked so great to slide across the carpet and build up a ton of static charge that we would play static electricity tag. And it would just zoom across the carpet and zap my brothers, and you could get it to shoot like so far. One other story. Right out of college, I taught high school for a few years in a boarding school. Had to teach in a coat and tie every single day. And this one administrative hallway had a water fountain and I used to wear these nice dress shoes because you had to dress up and, like I said, coat and tie. Every time I would walk down this one hall and get a drink, I would get shocked because the shoes and the carpet charging by friction occurred. I would become charged, and then when I touched the metal of the water fountain, I got shocked. So one day I was like, I'm sick of this. So rather than touching it, I had my coat and I bunched up my sleeve so that I had a bunch of fabric between my skin and the metal, touched it down, it was good. And then when I went to get a drink, I totally shocked my tongue. I forgot that water is actually a pretty good conductor, and I had charges flowing from the water fountain through the water onto my tongue. Okay, let me write down some notes for you. Okay, and I'm just going to kind of write these next to it just so that you have time to copy them down. So like I said, 3 different ways of charging an object. You've got charging by friction, contact, and induction. So for charging by friction, basically friction causes electrons to get transferred when one material rubs against another. Pretty much anytime you get some kind of static shock, this is occurring because of charging by friction. So whenever you think of like static electricity or things like that, it's 2 materials rubbing together. One of those materials happens to want to lose electrons. The other one happens to want to gain electrons. So when they're rubbed together, the electrons are transferred from one to the other, and they both become charged. Whichever one lost electrons is positively charged. Whichever one gained electrons is negatively charged. So charging by contact. This is really just touching a charged object to a neutral object. And in this case, charge is transferred by touching them together. So usually whenever you have a static shock, you have both of these happening. Because of charging by friction, you become charged. And then in the process of touching something else, that charge is transferring off of you or onto you. How do you know if it's going to go off of you or onto you? It's always electrons that are being transferred. So if you're negatively charged, that means you have a bunch of excess electrons. So when you touch something, the electrons will flow off of you. If you're positively charged, that means you've lost a bunch of electrons. So then when you touch a conductor, electrons would flow onto you. Okay, and then charging by induction. This is the process of charging one object without touching it to another object. And this should be to another charged object. So charging by induction. Charging one object without touching it to another charged object. So let me show you another example just right here. So let's say I have a big old just conducting sphere, metal sphere. There are billions and trillions of atoms that have protons and electrons in them. I'm just going to draw some positive and negative charge. So this is just representing some of the billions and billions of protons and electrons and positive ions and negative ions and so on. It's neutral though. It has the same number of positive and negative charges. Now I bring a negatively charged rod nearby. So I got a wool rod that I charged negatively. What is that going to do to the charges on the sphere? Well, it's going to repel the negative charges, and it's going to attract the positive charges. So the end result is I'm going to have a bunch of negative charges move over to this side, leaving one side positively charged, one side negatively charged. It's still neutral. I have not added any charge and I have not removed any charge. The charge has just rearranged itself. Now, if I were to touch this end with some kind of conducting wire, then I could let that negative charge flow off of it. And that would be sort of the next step is while this rod is still nearby, now you touch it with some kind of grounding wire. Basically just something that allows the charge to flow off of it. And what's going to happen is a bunch of the electrons are going to flow off of the metal sphere. And then the end result is the sphere has lost electrons and become positively charged. Friction, fields. Okay, let me share with you one or two little. Let me share. I want to show you something. Okay, so just another quick little example of static electricity charging by friction. So when you scuff your feet across a carpet, they added all these sound effects that he used to have. So you are, in this case, he's scuffing electrons off of the carpet onto him. What it's not showing is the carpet is now positively charged because it's lost a bunch of electrons. So now he has a bunch of excess negative charge. He's negatively charged. And then if you get close enough to a conductor, one more time. Gazouch. Okay, and then one more time, I'm going to come back to this. But when you rub a balloon on your hair or on a sweater or something, you can get electrons being transferred to the balloon, leaving the balloon negatively charged. So now the balloon would be attracted to the wool because balloon's negative, the wool's positive. But if you notice the wall here, the wall is neutral. But I can get a balloon to stick to the wall if the balloon is charged. Why? I'm going to write this down in a bit. But even though the wall is neutral, if I bring a charged balloon, watch what happens to the charges on the wall. The negative balloon repels a bunch of negative charge away, leaving the side of the wall closest to the balloon positive, the side farthest away is negative. Now, what's going to happen is, let me just annotate this real quick. The negative part of the balloon is attracted to the positive side of the wall here, but it's also repelled away from the negative part. But remember, force depends on 1 over distance squared. The smaller the distance, the bigger the force. So the distance between the negative balloon and the positive wall is smaller than the distance between the negative balloon and the negative part of the wall. The smaller the distance, the bigger the force, which means that the attractive force is stronger than the repulsive force. I'm going to come back to that. Stop, share. Okay, let me just pause for a second. This always happens to me and I hate it. Ha, 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 ha. Oh, yeah. And actually, I should have taken a picture now. At many different gas stations, you will see a little warning that says, warning, do not get back in your car, fire hazard. And that's because when people get in their car, they can actually get charged. Oh, where's that video? There's a video I have of somebody who gets out of their car while at a gas station, goes near the gas tank and catches the gas tank on fire because they got charged. Let me spend 5 seconds seeing if I can find this. Videos and applets.
Gas tank caught on fire?
Yes. Bowling ball, gas station warning, high voltage cable and sonic boom, standing boom traverse, human added colors. Like, oh, okay, I will have to find it. Oop.
Okay, question. Okay, so one time my hand caught on fire and my hand, yeah, and they said it was because I was wearing a metal ring on my finger when I plugged a cord into an extension cord and it blew up, and then I guess it like conducted. Yeah, it was
because you were wearing a ring.
Yeah, they said because I was wearing a metal ring that it conducted more. Like they said that a hand wouldn't typically catch on fire like that.
No. I'm perplexed.
Is your hand okay?
Yeah, my hand's fine now. It was like,
oh my god!
It was like a year ago. It
so
was
wait,
like
you were plugging something into an extension cord?
Yeah, I was at work and I was plugging like a warmer, like a stove warmer into an extension cord, and that short circuited, and then it blew up in my hand and my hand caught on fire.
Wow.
And when I went to the emergency room, they're like, oh, it's because you had a metal ring on and it conducted or something.
Wow. Yeah, I had never heard that before.
I don't know.
I'm looking real quick. All right, I don't know where that is. Such a good video too. Let me just real quick. Could I boop, 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 boop. If you were me, where would you put a super good video like that? Videos.
Did you like it on YouTube?
Wait, tank implosion, siphon, static. Oh, that's a shockwave file. Oh, optical camel, mega whoosh, mock, Brownian motion, amazing jump. Oh, here we go. Wait, is that the video? Oh, static. Okay. Yay. Let me share this. VLC. So let me just fast forward a bit. So she goes to the gas pump. Everything's fine. Problem is here, she gets back in her car. So in the process of either getting into her car or getting out of her car, charging by friction occurs. So now she is charged. Look how calm she is. She's just like, I'll put it down. No
You
big
just
deal.
scarred me for life.
What's that?
I said you just scarred me for life. You just gave me a new fear of ever dumping gas. Oh my God.
A couple things. One, what's happening is, if you've ever seen like the air around your gas tank look like it's shimmering, it's because as the liquid gasoline is flowing into your tank, you also have gasoline vapor, gasoline in gaseous form. So right around the tank here, you've got this gasoline vapor. And then when she got close enough, basically, back a second. I have to make you keep watching this over and over again. What she should have done is, as soon as she got out of the car, touched metal far away from the gas tank. But as she got close, she's got a bunch of negative charge or positive charge. She's wearing insulating shoes, so the charge isn't flowing into the ground. And so when she came near the metal conductor, charge went either from her to the car or from the car to her, passing through the gasoline vapor and then causing it to ignite.
The moral of the story is touch the car door before I touch the gas pump.
Well, what they say is, one, once you start pumping gas, you shouldn't get back in your car. So just stay out of your car the whole time. But if you did go into your car, touch a metal surface as soon as you get out of the car, far from the gas tank.
Why is there like warnings? Is there warnings and I've just never seen them?
Now there are warnings.
Really?
And I think part of it is people didn't used to get back in their car, right? You didn't have cell phones to check and things like that. You got out of the car and you just stayed there. So.
But it's cold outside. That's my biggest issue. But
Okay. Let's go back to this Pitfall. Let me Control N. Alt N. Okay, I'm gonna try this again. Okay, so right now this is a neutral pith ball. It's really just a very, very light styrofoam ball that has an aluminum-based paint around it that's a conductor. Rod is not charged. I'm not, oh, maybe it was charged. I'm not getting anything happening. But once I rub the wool to the rod's going to become positively or negatively charged. And what I want to show you is I'm using a negatively charged rod to attract a neutral object. Look at that, look at that. Oh, oh. I think I told you on a good day, I can get this to, again, it's raining today, but you can get this to stand straight up. Pretty impressive. And while I'm here, balloon, gray hair, sticking on a surface. And one, do I have? Remember that rubber is actually a good insulator. So what I'm going to do is put a little X right here. And what I'm going to do is charge the side of the balloon opposite the X. So I'm going to rub it and then show you that the charge is going to stay where it is. Meaning if I rub this part on my hair, this part of the balloon is going to become charged. And since it's a insulator, not this part. So then if I You see that it'll stick to that part, but then if I try and turn it around, it will not stick to the other side. Only the side that was charged. Yay, physics fun. All right, so let's talk about something called electric polarization, or something becoming electrically polarized. So let's do a little new thing here. So let's talk about how can a charged object attract a neutral object. And let me cut to the chase. And the answer is the neutral object becomes electrically polarized. And this basically means the charge has separated. So here is a little diagram just of the pith ball. P-I-T-H. Again, all it is just a very, very light styrofoam ball, and it has some sort of aluminum-based paint on it, something that's a good conductor. The pith ball is neutral. Same number of positive and negative charges. So pith ball, it's neutral because it has same number of positive and negative charges. Now, what happens is if I bring in this case, let's say a negatively charged rod nearby. So whenever I draw this, this is just showing that the rod is negatively charged, not that there's only negative charge on it, right? If you were to try and count the number of electrons and protons in this rod, it would be in the, I don't know, trillion, some huge gigantic number. So this is just showing that there's some excess negative charge. Well, what that is going to do is, the reason it attracts the pith ball is because it causes the charges on the pith ball to separate, and one side becomes positively charged and the other side becomes negatively charged. So in this case, pith ball is still neutral, but charges have moved to opposite sides. So one side is positive and the other side is negative. We call this electrically polarized. Now, opposite charges attract, like charges repel. So if I look, this positive part of the pith ball is getting attracted to the negative rod. At the same time, this negative part of the pith ball is getting repelled away from the negative rod. But the force depends strongly on distance. The smaller the distance, the bigger the force. The bigger the distance, the smaller the force. So the attractive force is stronger because the positive part of the pith ball is closer to the rod than the negative part. So the attractive force is stronger because the positive part of the pith ball is closer to the rod than the negative part. If anybody has a small balloon like this, or a comb or something like that, let me show you. Well, let's just do a clicker question. But this is something that I'd like you to try if you can. It's a great little demo. I can't really do it here. But if you get a charged object, like in this case, a negatively charged balloon or a rod or something like that, it can attract a stream of water. And the reason is it can cause individual water molecules to become polarized also. So what ends up happening is, actually, you know what, before I get to this, let me just go back for a second. I apologize. I'll touch on one other thing. So I was just kind of writing this down before, is that if I've got a pith ball here and I bring a negatively charged rod nearby, the rod causes the charges on the pith ball to separate, because in this case, the pith ball was covered with a conducting paint. It had a conductor on the outside. Question though is, what happens if the neutral object is an insulator? In an insulator, charge is not free to move from one side to the other. Ooh, and in fact, let's try a little demo here. Oh, let's stop the share for a second. Alt-N. What I want to do is just grab a couple of pieces of paper. So paper is a insulator. Doesn't have a bunch of charge, which is free to move around. This is something that you can try at home. If you have a comb and you rub your hair, you can get your comb to be charged. Here, I'm just going to use the balloon. And hopefully you'll see these little pieces of paper do something. I don't know how well you can see that, but they are being attracted to it. Woo! Wow, that was fascinating. So here's the question is, how can a charged object attract a neutral object, which is an insulator? Well, again, the object becomes polarized, but in this case, it's individual atoms and molecules that are induced into becoming more positive and negative. So rather than, like in the case of the pith ball, you actually had a conductor on the outside, which means there were a bunch of free charges that could move. So I could have a bunch of electrons actually moving to one side, making this side negative, the other side positive. But if it's an insulator like paper, paper doesn't have a bunch of free electrons in it that can move to the other side. However, you can have individual atoms and molecules can become polarized also. So whenever you see this little picture here, the way this is drawn in the book where you've got plus minus, this is an individual atom or molecule. That is neutral, but electrically polarized. In essence, what it means is I have an individual atom where the charge is not uniformly distributed, where I've got one side of the atom is more positive than the other side. What it would look like, let me just go here real quick. I'll keep a picture of this I can show. No. All right. So what ends up happening is, even though in a piece of paper, you do not have electrons that can move from one side of the paper to the other, in each atom, the electrons have a bit of freedom to move around, and I can have individual atoms that become polarized. So if this is like a piece of paper here, then each little paper molecule, whatever paper's made of, can become polarized. And again, closeness wins, and the object's going to be attracted to the rod because this little positive part of the atom is ever so much closer than the negative part, which means the attractive force is just a little bit bigger than the repulsive force. I mention this because if you have a charged object, like a balloon that you can charge, or if you have a comb you can comb your hair, have a very, very thin stream of water, and you'll find that you can attract the water towards this charged object. And it's really quite fascinating when it works. And let me just see, do I have a picture of it in my PowerPoint slide? Reduce charge. So here's just a picture of, oh, am I sharing this? I don't even know what I'm sharing right now. All right, I am sharing that. Okay, so you can get the water to curve a pretty impressive amount. And it is doing that because the water is neutral, but again, the water molecules can become electrically polarized. And if you've taken some chemistry, water is actually a polar molecule, which means one side is already more positive than the other side. So what happens is, let's say the thin rod bends towards a negatively charged rod, or the thin stream of water bends towards a negatively charged rod. If instead I bring a positively charged rod near the stream, will it bend in the opposite direction? Will it bend in the same direction? Or will it not bend at all? So if this rod is negatively charged, I can get the water to bend towards it. And the reason is because it attracts the positive part of the water molecules. Well, what if instead I bring a positively charged rod nearby? What is that going to do? Well, the answer is it's still going to bend in the same direction. One, let me just say that you cannot have a charged object repelling a neutral object. You can get a charged object attracting a neutral object. So in this case, we're talking about water. It's still going to attract it. The only difference is the side of the water molecule that's closer to the positively charged rod is now going to be negative, and the side farthest away is going to be positive. So you're still going to get it bending towards any charged rod, It's just which side is positive and which side is negative. It's going to depend upon the charge of the rod that you're using. All right. Last thing I want to just talk about real quick is electric fields. I need, let's just use these balloons. Ooh, let's just use one of these positive and negative. I touch on this just a little bit because we need to understand electric fields just a tiny bit to understand light. So let's say I got a positive charge here and I've got a negative charge here. Maybe this is a proton, this is an electron. We know that these two objects will attract each other because they have opposite charges. For the longest time, we didn't completely understand why they attracted each other. And physicists were very disturbed by the fact that you could exert a force on another object without touching it. This demonstration that I did with the Pith Ball, that kind of demonstration really frustrated and pissed off and annoyed scientists because they called it spooky action at a distance. How can you attract an object without physically touching it? Like if you wanted to exert a force on an object, you would push it, pull it, you would exert a force by making contact with it. How can you exert a force without making contact? Well, they called it spooky action at a distance. So the old thinking was these two charges are exerting a force on each other. But here's the new thinking, and I'm not going to go into this in great detail. I just want to bring it up and talk about it conceptually. As soon as I have a charge somewhere in space, this charge has physically altered the space around it in a way that we as humans cannot sense, but it creates an electric field. And the electric field created by this charge will then affect other charges nearby. So old thinking was this positive charge attracts this negative charge. The new thinking is this positive charge sets up an electric field surrounding it, which then it's the electric field from this charge that is exerting a force on this charge. So let me just share the screen for a second. Okay, so here we are in deep space. There's nothing. And now I take a positive charge and I just plop it down into space. As soon as I do that, I have physically changed the space around that charge. I've created a force field called an electric field. And then that electric field will then go and exert forces on other charged particles. Similar to a magnetic field. You've probably, let me just stop this for a second. You have probably experienced magnetic fields as a kid where you just have a magnet and you put some iron filings over a piece of paper and they kind of line up with the magnetic field of the magnet. We can't do that as easily with an electric field, but there is a change in the space around a charged object because of the presence of that charged object. Just like if I put a magnet near a bunch of iron filings, that magnet will affect the iron filings. What we now know is that that magnet affects the space around it, creates a magnetic field, and it's that magnetic field that exerts a force on iron filings. So as soon as I put a charge somewhere in space, or a couple charges, these charges have physically altered the space around it, and it's created a force field called an electric field that will then affect other charges. Now, we as humans do not have any organ that senses electric fields, but there are other animals that do. Sharks can sense electric fields, eels can sense electric fields, there's other animals that can, and they can use that to hunt. And there's other animals that can sense magnetic fields. Chapter 24 is all about magnetism. And what we know is that one of the ways that homing pigeons and other birds navigate is they have a little organ in their brain that's basically just like a compass. And the Earth's magnetic field varies at different spots on the Earth. And birds can use that changing magnetic strength to navigate. So in terms of what to know about electric fields, that's not what I wanted to do. Let me just say a few things. Is, you know what? I don't think that I'm going to go into electric fields in detail. I just wanted to touch on a little bit of it. What I think I'd rather do for about 7 or 8 minutes is just quickly touch on the homework for chapter 22. So just so you know, we're done chapter 22. I was just going to touch briefly on electric fields like I did. Chapter 22 homework and quiz is due next Tuesday. If you're watching this on YouTube, highly recommend you pause the video now, work on the homework for chapter 22, and then come back and check out this video. So what I'm going to do now is just spend about 7 or 8 minutes quickly going through the homework for chapter 22. Oh, actually, what do I've got? 9 minutes. All right, let me just touch on 1 or 2 of them. Share screen. Actually, I think I can answer them all quickly. I'm just not going to write them down. Question 1. Why are objects with vast numbers of electrons normally not electrically charged? The simple answer is most objects have exactly the same number of protons as electrons. The number of electrons in your body is insane, but so is the number of protons, and so is the number of neutrons. So for the most part, atoms, objects usually have the exact same number of protons as electrons. 2. Why do clothes often cling together after tumbling in a clothes dryer? Simple answer, charging by friction. As the clothes are getting dried, you constantly have clothes sliding against the inside of the dryer, rubbing against each other. You have charging by friction occurs where the charge can get transferred from one set of clothing to another or from the dryer to the clothing. Either way, the clothing gets charged, and then it can attract other objects, even if they are neutral. 3, strictly speaking, when an object acquires a positive charge by the transfer of electrons, what happens to its mass? What happens when it acquires a negative charge? Think small. Electrons have mass. Even though it's tiny, they have mass, which means if you gain electrons, you gain mass. If you lose electrons, you lose mass. So an object becomes positively charged by losing electrons, which means it lost mass. How does an object get to be negatively charged? By gaining electrons. Anytime you gain electrons, you gain the mass those electrons had. So an object is positive, it's lost a little bit of mass because it's lost electrons. When an object is negative, it's gained a little bit of mass. Let me come back to 4. 5. When one material is rubbed against another, electrons jump readily from one to the other, but protons do not. Why is this? Simple answer is protons are relatively weakly bound. Did I say protons? Sorry. Electrons are relatively weakly bound. Protons are trapped inside the nucleus by the strong nuclear force. It's always electrons that are getting transferred. And in fact, it's always the outer electrons on the outside of the atom, not the inner one. 6. How does the magnitude of electric force compare between a pair of charged particles when they are brought to half their original distance? 1/4 and 4 times. So again, Coulombs law says F equals K Q1 Q2 over D squared. But we're really just imagining and thinking about the fact that Force depends on 1 over distance squared. So I think most people are pretty clear about the fact that the bigger the distance, the weaker the force. But since it depends upon distance squared, if I go twice as far away, the force changes by a factor of 4. If I go 3 times as far away, the force changes by a factor of 9. So when they are brought to 1/2 their original distance, then in this case, the force is going to be bigger by a factor of 4, right? They're twice as close. Force increases by a factor of 4. When they are brought to 1/4 their original distance, they are 4 times closer, which means the force is 16 times greater. And then to 4 times their original distance, it would be 1/16. And 7. When you double the charge on both particles in a pair, what effect does this have on the force between them? Does the answer depend upon the sign of the charges? So here, the force depends upon Q1 times Q2 divided by d squared. If I were to double one of the charges, the force would double. If I were to double just the other charge, the force would double. But if I double both charges at the same time, since it depends upon the product of the charges, if I increase one by 2, factor of 2, and the other by a factor of 2, I've increased the force by a factor of 4. So when you double the charge on both one, force increases by a factor of 4, and it doesn't depend upon the sign. Right? If they have same sign, it's going to be a repulsive force. Opposite sign is going to be an attractive force, but it doesn't matter in terms of getting the force to be 4 times bigger, whether the charges are attractive or repulsive. 8. If you rub an inflated balloon against your hair and place it against the wall, by what mechanism does it stick? Well, what happens is the balloon polarizes the wall. So let's say the balloon is negatively charged. That's going to cause the charges on the wall to separate, leaving one side positive, one side negative. The fact that the positive part of the wall is closer to the negatively charged balloon means the attractive force is going to be stronger than the repulsive force. 8. A friend says that the reason one's hairs stand out while touching a charged Van de Graaff generator is simply that the hair strands become charged and are light enough so the repulsion between strands is visible. Do you agree or disagree? Let's stop this. Alt-N. Here's a case where your friend is correct. So let's see if I can get these to stand up. It's working a little bit. I don't know how well you can see it, but in class this works really well with some students' hairs. Anyway, Alt-N. The answer is the student is correct. When you're touching it, you can get the negative charge from the Van de Graaff to transfer through your hands into your hair. And since like charges repel, your hair repels itself. And since it's light enough, it can actually stand up. Okay, just in terms of timing, I'm going to just skip answering the 4th one. You still have to do it, but I will touch on that probably just a little bit on Tuesday, just to quickly answer that one. That is it for chapter 22. I need to stop now so I can get ready for my next class. Aaron, Eve, thank you so much for joining. Have a wonderful weekend, and I'll see you on Tuesday. You're welcome. Thank you.